This video presents our work, which describes a white box methodology for simulating and visualizing optical phenomena elicited by negative refraction. Our perception of the world is shaped by light and the path that it takes. For example, this glass sphere reveals an inverted image of the scene behind it. When light moves between different materials, its path bends in a phenomenon known as refraction. This is what causes the sky to appear at the bottom of the glass sphere rather than the top in our photograph. This bending is governed by a material property called the index of refraction, denoted with Greek symbol eta. In simple terms, this parameter describes how strongly light is bent at the boundary between materials. All known naturally occurring materials have a positive index of refraction. In 1968, Victor Veselago theorized materials with a negative refractive index, or NIMS, that could bend light in unconventional ways. Decades later, engineered metamaterials made these properties realizable, enabling applications such as cloaking and hyperlenses. To understand the effects of these specialized materials on light propagation, we consider light instant at an interface and transmitting into a NIM. At this boundary, light refracts on the same side of the surface normal rather than the opposite side as observed in conventional materials. We term this phenomenon negative refraction. While Snell's law still governs refraction at a NIM interface, the standard Fresnel equations are no longer applicable. This graph shows an example where the standard equations violate energy conservation by predicting reflected energy exceeding the total incident energy. To resolve this, the Fresnel equations can be re-expressed in terms of wave impedance, yielding a physically valid methodology that can be seamlessly integrated into a Monte Carlo path tracing framework. See our paper, A Window to the World of Negative Refraction, for details. As NIMS have not been observed in the visible range, no ground truth exists for quantitative evaluation. We instead evaluate our methodology using canonical optical scenarios to qualitatively compare our simulated results with visual and analytical observations reported in related works. We first consider a classical refraction scenario with a straw inside a glass containing different media. In the liquid NIM case, we see the straw bend the opposite direction at the interface. Magnification and distortion effects are also clearly visible from the top view. We next examine transparent spheres under varying refractive indices. These examples show how NIMS modify caustics, image inversion, and create distinct inner and outer regions. These results are consistent with qualitative observations reported in related works involving the visualization of NIMS. Having established predictability, we now showcase the applicability of the described methodology. We next consider an observer submerged in a swimming pool viewing a Snell's window at the surface. We compare renderings of a pool containing a conventional water medium and a liquid NIM. In the latter case, negative refraction introduces distortions and modifies the apparent arrangement of objects above the interface. We also observe differences in caustic patterns under sunny conditions. For details on Snell's window, please refer to our paper. Finally, we vary the material's electromagnetic parameters which affect the Fresnel response and the balance of reflected and transmitted light. Higher magnitude negative permeability increases reflection, darkening the scene and revealing the pool floor within Snell's window. In this work, we presented a physically based methodology for simulating the optical effects of negative refraction across a range of scenarios. This highlights the applicability of predictive rendering in the study and visualization of NIMS.